Hi everyone, this is task 5, question 4, and this is going to be part C, which is a little bit more complicated. Okay, so let's look at how we can find the order of reaction with respect to P and Q first before we write a rate equation and calculate its value. Okay, first thing to notice, I think, is that the values for the rate are no longer friendly numbers, or they don't seem friendly numbers to start with. But if you look at what they are, 0.00200, so let's say 200, 400-ish, 600, 1600, and when you start to compare those, you see that there is quite a good relationship between 2, 4, 6 and 16. So that's going to be a hint at the factors that the concentrations increase or decrease by. Okay, let's try to find the order with respect to P first of all. Okay, well, we can see that the concentration of P there increases by a factor of 2. Q stays the same. So how's the rate increased? Well, it's increased by 0.00398 divided by 0.00200, which is approximately 2, just over 2, but that's an increase of a factor of 2. So as P has increased by a factor of 2, the rate's increased by a factor of 2. So the order with respect to P is first order. So let's find the order with respect to Q. So what we can see now is that we've got a choice of experiments to compare. And I think the more that you do these examples, the more that you can look quickly at a series of experiments and decide which sets to compare. And that can be the most efficient set to compare. So the ones I'm going to compare are experiment number 2 and experiment number 4. So you can see that the concentration of P has increased by a factor of 2, and the concentration of Q has also increased by a factor of 2. And the reason why I'm having to choose a pair of experiments where both concentrations have increased is that there isn't a set of experiments that you can compare where the concentration of P has remained the same whilst Q has doubled. So you're going to have to take into account how the concentration of P and its order affects the rate as well. So we can see that P has increased from 0.2 to 0.4, which is doubling. We know that it's first order, so that means we should expect the rate to increase also by a factor of 2, so that's 0.00398 times 2, which is 0.00796. That's what we expect the rate to be, okay? But we can see that it's not. It's a lot higher than that, and that must be to do with the concentration of Q increasing. So the concentration of Q is increased by a factor of 2, and it's increased from 0.00796, that's what it should have been, based just on P, to 0.01598. So what increases that? 0.01598 divided by 0.00796, and that's a factor of 2. So as Q has increased by a factor of 2, so the rate has increased by a factor of 2 as well. So that means the order with respect to Q is also first order. That means now we can write our rate equation. So our rate equation will be rate is equal to K, the rate constant, multiplied by the concentration of P and the concentration of Q. They're both first order. Let's find a value for the rate constant. So K is equal to the rate divided by the concentration of P multiplied by the concentration of Q. Again, it doesn't matter which set of experiments you choose, so I am going to use the bottom one, so the rate 0.01598 divided by concentration of P, 0.4, multiplied by the concentration of Q, 0.2. Work all that out, and it gives you a value of 0.200 to 3 significant figures here. And the units, moles to the -1, decimeters cubed, seconds to the -1.